um, talk. Joe, I've been working for Joe for quite some time. It's a pleasure to have him here. He graduated from Berkeley in some time ago, and then
2017.
What?
2017.
2017, and then he went to start a postdoc at Princeton with Amit Singer, which was also my advisor, and that's how we met. And then he went to T. Austin and joined as assistant professor, where he is now. And he's applied mathematician that uses computational algebra to tackle a variety of problems, like tensor decompositions and the reconstruction problem in cryo-EM, and other problems like this one.
Thanks a lot, Joao.
Yeah. Just something before the talk starts. If you need to ask a question, just let us know and put your hand in the air, because you need the microphone to ask a question.
Yes. Thanks a lot. It's been really nice visiting here. Please do ask questions. I don't think that these slides are actually long enough to fill the time. So definitely ask questions. So the informal title is Fantastic Lifts and Where to Find Them, with the subtitle of The Effect of Parameterization on Non-Convex Optimization Landscapes. So this is joint work with Eitan Levin, who's a talented PhD student at Caltech, and Nicola Bumo, who's on the faculty at EPFL. And this corresponds to the archive link there. So for motivation, we'll start by thinking about low-rank matrices. So suppose we consider an optimization problem where we wish to minimize a cost f of a matrix variable x, which is m by n, subject to the constraint that the rank of x should be less than or equal to r. Okay, so just the optimization over low-rank bounded rank matrices. So this is a ubiquitous problem with lots of applications. For example, in recommender systems, in the context of matrix completion, or when solving large-scale linear matrix equations, for example. So those are linear systems of equations where the variable is a matrix, and if it's very large scale, you might like to impose low rank structure on the variable. And in a variety of other applications, this comes up in. Okay, so we'll consider this where the cost function f is a smooth function on all of r to the m by n. So f is nice and differentiable. This constraint, though, is not smooth. Right? So bounded rank matrices do not form a smooth set in r to the m by n. They form an algebraic variety which has singularities at the x's where the rank is strictly less than r. So it's not a manifold, the constraint set here. It has singularities when the rank is strictly less than r. Okay, so, but nonetheless, this is very ubiquitous. So minimizing a smooth function over a non-smooth set. So how could you tackle this? There are different possibilities, but a simple and standard one is to parameterize bounded rank matrices. So a matrix X of rank less than or equal to R, it's of rank less than or equal to R if and only if there exist matrices L and R of size M by R and N by R such that X equals L times R transpose. Right, so we can exactly parameterize bounded rank matrices as L times R transpose. And what's nice about this, L and R have no additional constraints. So they just live in Euclidean space, which is nice and in particular smooth. Okay, so L and R are in a big Euclidean space that's smooth. And so the question we want to ask is, if we try to solve the problem in the parameters L and R, and we find a good solution from the point of view of the parameters, will those L and R map to a good X, a good solution in the original space X of bounded rank matrices X? Okay, and so I'll have different meanings for the word good here during the talk, but the general flavor is this. We want to ask, if we have a potentially complicated constraint set, which we parameterize, and solve a problem in parameter space, will it map to a good answer in the original space? That's what we want to focus on here. All right, so yeah, what do we mean by good? Well, one thing we could mean by good, the most basic maybe, is first order one critical, or first order critical. So for L and R, what it means is that we'd like the gradient to be 0. Right, so that would be a one critical LR. So we might ask, will such a point where the necessarily map to an X which is one critical for the original problem? And that actually is not true for this parameterization. Okay, so in fact, just here, the LR transpose parameterization, it can happen that you can have a cost function and L and R where the gradient for L and R is 0, and yet the gradient in the corresponding X is negative. The gradient correlates with a vector in the tangent cone to bounded rank matrices. So in other words, you can map to a non-critical matrix. Okay, and this is sort of an interesting failure here. But some positive news is that actually two critical LR pairs necessarily map to one critical matrices X. So by two critical, what does it mean for L and R? It simply means that the Hessian should be semi-definite, or so if that's the case, then in fact the corresponding X always will be a first order critical point in the inbounded rank matrices. And this is a fairly recent result of Ha and Barber from 2019. So, yep.
The result is strict or non-strict? Like, is it strictly positive or?
No, it doesn't need to be strictly positive, just positive semi-definite. Yeah. Yeah, that's what we mean here by two critical. Okay, so this is a property purely of the parameterization. LR goes to LR transpose, because actually for any cost function f where the questions make sense, so f has to be sufficiently differentiable, twice differentiable, then we have this this holding. So it's really a property of the parameterization. So that's what this talks about, parameterizations. And so let's illustrate it in some pictures. So in the example I've been discussing so far, we started with a subset of a linear space. And that was all the matrices X of rank less than or equal to R. We have here some cost function on this, which is real valued. We took a parameterization of this subset. So the domain of the parameterization here was, in particular, a smooth manifold. It was a product of Euclidean spaces. And the map was smooth from the smooth manifold into the ambient linear space where our original subset lives, right? So LR goes to LR transpose. That's a perfectly smooth map, and it parameterizes our subset in the sense that its image is precisely the subset we started with. Okay, and we considered lifting the original cost F to a cost on the in the parameter space. So here we'll call that G. So G of L comma R, by definition, is F LR transpose. Okay. So that was the nice thing about doing this, in particular parameterizing by a smooth manifold, is that we have algorithms for optimizing on smooth manifolds. So more generally, we'll have upstairs a smooth manifold M, and it's going to be parameterizing via a smooth map that I'll throughout the talk call phi, some subset X of a linear space E. That subset X, maybe calligraphic X, may be non-smooth and quite complicated. So we'll be studying maps phi from M to X inside E, and using such a parameterization to lift cost functions F on X to cost functions on M. G, we'll call the cost function on the parameter space G, and it simply is F composed with phi. Okay, so the conditions that we're placing on the parameterization here are very basic. We simply want its domain to be a smooth manifold. We want it to be a smooth map from its domain into E, and we would like its image to be X. That's all we impose. Okay, so there's lots of other examples of this besides the LR transpose parameterization. A simple one is that we can also incorporate positive semi-definite constraints on X. So our subset downstairs could consist of all n by n PSD matrices whose rank is at most R, satisfying some linear constraints. So this might come up if you attempt to do if you think about solving an SDP with an additional rank constraint. That might give you this subset calligraphic X downstairs, and a natural way to parameterize that is as RR transpose, where R is an n by R matrix, and R needs to satisfy certain constraints to ensure that RR transpose satisfies the linear constraints in the SDP. So it turns out that that often the linear constraints in X will lift to will result in a manifold in R when we lift those constraints. So okay, so this is another example, just using RR transpose. Here's one more key example provided by neural networks. So if we think about a neural network, it's parameterized by weights and biases. And let's suppose the activation function here is smooth. Then the weights and biases are smoothly parameterizing some class of functions, like all the functions representable by the neural network. and we can lift optimization problems over that class of functions to optimization problems over the weights and biases. Okay, so in this example, it's of a bit of a different flavor than the last two ones, because really the space downstairs here is extremely hard to describe, the functions that are represented by the neural network. And really, it's extremely natural you almost have no choice but to work with the parameterization in this example. So you don't have the function space otherwise. Okay, but it fits into this same framework so long as you have a smooth activation function. Okay, I want to also mention that it's actually not important that the linear space downstairs be finite dimensional for any of our work. So it's okay if we're in an infinite dimensional setting for functions. Okay, so again, this is the general setup of the talk. We have a subset X downstairs in a Euclidean in a linear space E. It's parameterized smoothly by a map phi with domain M, and we're going to be lifting problems on X to problems on M. And on M, we can apply manifold optimization algorithms. Okay, so any questions about this setup? No? Okay, so once we have this parameterization, problems come in pairs. Right? So any optimization problem on X can be lifted to one on M. So we'll call our cost functions f on X and g on M. And what we've done in this work with Eitan and Nicola is address this question. When is it that good solutions in parameter space map to desirable solutions in the original space? And we really want to study this. We want to view this as a question of the parameterization itself. So we're going to ask that this holds for classes, wide classes of cost functions. Okay. So we'll have three types of good points. Now, the best point for a minimization problem is a global minima. Next, you might want a local minima. Thirdly, you hope that at least you'll get a critical point. And that critical point could be one critical or two critical, for example. So we'll think about this question for these types of good points. Okay, so in this general context. Okay, so this is really, okay, that went away. So for global minima, it's actually very simple to understand. So a global minima in parameter space always maps to a global minima in the space X, simply because we're assuming that phi parameterizes X. It's phi of M is equal to X. So So Y being a global minimum upstairs, if you think about it, is equivalent to phi of Y being a global minimum downstairs. So for global minima, there's really nothing much to say. If you can find the global minima in parameter space, that's great. That's definitely the global minima that you want for the space X. But I mean, for most of the problems we're interested in are non-convex, and we can't guarantee that we're going to be finding global minima. So the question, it's also very important to understand what happens with local minima or critical points, because often those are the only types of solutions we can guarantee that we'll find. Okay, so let's think about what can actually go wrong here. Suppose our space X is the shadow that you're seeing in this figure. So it's the so-called nodal cubic. in the plane. So x is the shadow. It's some curve in the plane. Turns out to be defined by, you can define it by a cubic equation. And it's sort of this alpha curve in the plane. So suppose that's our x. We can parameterize that by a curve in R3, which is smooth. And that's the curve that's in bold that you see in the figure. That's M. So for a very benign type of cost function here, namely a linear cost function, f, down in the plane, it can happen that a local minimum, when you lift this to the smooth curve in R3, a local minimum need not even map to a critical point down on the alpha curve. So in this example, I don't have all the equations, but basically it can be, one can have a linear, start with a linear cost f such that one of the points mapping down to the node, one of the points upstairs in M mapping down to the node is a local minimum on the smooth manifold, and yet the node is not even a local minimum, or is not even a critical point. Intuitively, what's going on here is that upstairs in the smooth manifold, you can only move in a direction that corresponds to one of the branches passing through the node down in X. So somehow in the space X, there's another branch along which you can move, and it makes it so that the node is not even a critical point. And so this is sort of the basic mode of failure, where there can be extra directions of movement in the space X. Okay? So let me know if you have any questions. Okay? So, okay. All right, so let's discuss some properties of lifts. Okay, so this is probably the most important slide in the talk. So we study three main properties of parameterization's phi. One of them we call local implies local. And so phi, the lift, satisfies local implies local if, for all continuous cost functions f, y in the manifold M is a local minimum if and only if phi of y in X is a local minimum. Sorry, it's an implication. Sorry, yeah. So y is a local minimum implies that phi of y is a local minimum. Okay, so we summarize this by saying local. The lift satisfies local implies local. A local minimum in parameters necessarily maps to a local minimum in the original problem. Okay, and so because we're taking this, we're going over all cost functions here. This property just depends on phi. Okay, and I'll actually come back to this requirement that we go over, that we want this to hold for all continuous cost functions f. Okay, but okay, the second property we study is 1 implies 1. So here what we want is that for all differentiable cost functions f, y being 1 critical in M implies that phi of y is 1 critical in X. Okay? So that's 1 implies 1. And just to be clear, like, you can make sense of what 1 critical means for any subset X of E. So what you want is that the gradient of your cost, F, it's negative doesn't correlate with any of the infinitesimal directions you can make while staying in the set X. So in other words, the gradient should be in the dual of the tangent cone. Okay, the next property we look at is 2 implies 1. So here it means that for all twice differentiable cost functions f, y in M is 2 critical implies that phi of y is 1 critical in X. Okay, so for the LR transpose lift of bounded rank matrices, 1 implies 1 failed. I stated that, but 2 implies 1 did hold by work of Ha and Barber. Okay, and I mean these things, various different algorithms that you can run on smooth manifolds can be guaranteed to find second order critical points. So 2 implies 1 is relevant for algorithms because often we can find 2 critical points. Okay, so one of the main contributions is that we have full characterizations for these 3 properties. So local implies local turns out to be equivalent to phi being an open map. It's purely a topological property, and one direction here is kind of easy. If phi is open, so that means that it maps open neighborhoods in M to open neighborhoods in X. You can convince yourself that local implies local holds. The converse is actually took quite a bit more effort on our part, but it's also true. So this is an if and only if for local implies local. 1 implies 1 is kind of, it's well captured by the example that I showed with the curve. So it turns out to be equivalent to the differential of phi being a surjection at all points y and M. So the differential of phi is a linear map from the tangent space at a point y and M, and it takes values in the tangent cone at X. So this T sub phi of y of X is a cone a priori, and because X isn't necessarily a manifold. But what we need is that this needs to be surjective at every point y for 1 implies 1 to hold. That's an if and only if. But the thing is that this actually rarely happens. In particular, this can only happen if every tangent cone in X is a linear space, because the differential d phi is a linear map, and TYM is a linear space because M here is a manifold. So the image of this is always a linear space. So as soon as you have a tangent cone, a set X with a tangent cone that's not a linear space, this is 1 implies 1 is automatically failing. And that's actually how you can see that 1 implies 1 fails for the LR transpose lift, because bounded rank matrices have tangent cones that are not linear spaces. 2 implies 1 is quite complicated, and but you can see more in our paper. So we have an equivalent characterization for 2 implies 1, but we also have, it's a little bit unwieldy, so we also provided sufficient conditions for 2 implies 1 that are easier to check in practice, that enable you to show 2 implies 1 holds, as well as a necessary condition for 2 implies 1 that enable you to show 2 implies 1 fails by falsifying the necessary condition. So to say just a word on the flavor of this, 1 implies 1 involves the first derivative of phi. 2 implies 1 is going to involve second derivatives of phi as well. But it'll also involve the tangent cones down in X. that you can see the paper. So our proofs for these, as a nice byproduct, tell us that we don't actually have to look at such general cost functions f. It's in fact, for local implies local, we define local implies local as something that should be true of all continuous cost functions f. And you might think that that's an extremely stringent condition for a lift fee to satisfy. You've got to be good for all continuous functions f. But actually our proof shows it's equivalent to just for this to hold for all smooth functions f. So that's a little bit better. And for 1 implies 1, we defined it as something that should hold for all differentiable functions f. That's simply because we defined it that way simply because the condition 1 implies 1 makes sense for any differentiable function f. You just need to be able to talk about one critical and derivatives. But again, I mean, that seems like a stringent thing to require of phi. But in the course of our proof, we see that it's equivalent to 1 implies 1 holding for all linear f. So in particular, if 1 implies 1 fails, it's going to fail for a linear cost function. And 2 implies 1 is equivalent. It's equivalent to require 2 implies 1 holds for all convex quadratic cost functions f. So also, benign cost functions will violate 2 implies 1, and if 2 implies 1 is not true of the parameterization. Okay, so any questions at this point? Okay, good. So let me just say a couple words on this. So for 1 implies 1, you explicitly saw the tangent cone at x in the characterization. For 2 implies 1, the tangent cone is also important. So in examples to make our characterizations actionable, you actually need some knowledge of the tangent cones for the set x. And let me just remind you the definition of a tangent cone to an arbitrary subset x of E at a point x. It's defined this way. So it's the set of all vectors v in E that arise as limits of xi minus x divided by a scalar tau I for xi's in your set x, and some tau i's that are positive tending to 0. So it's just sort of like all limiting secants in your set. That gives you, so that definition makes perfect sense for any x. And in general, this is a closed cone. So cone, it's closed under positive scaling, and it's closed in E, but it's actually not necessarily convex. So we saw that already with the alpha curve. The tangent cone at the node in the alpha curve is a union of 2 lines. So this isn't always convex. We need to calculate this tangent cone for sets x of interest, or at least bound it. So we do require some knowledge of this tangent cone in using our characterizations, and that actually can be one of the hardest steps, saying what this tangent cone, saying things about these tangent cones. So for example, for neural networks, what is the tangent cone to the functions, to the space of functions represented by a neural network? That's probably hard to say things about. So I want to give you some applications of our results. So speaking of neural networks, one result is that there is always a smooth cost function. Okay, so this holds for any neural network architecture with at least one hidden layer and non-constant smooth activations. there's always a cost function with a spurious local minimum in parameter space. So this follows from some work of Pedersen and co-authors. So they showed that the parameterization provided by a neural network is not open. And that means that local implies local fails by and it fails for a smooth function. And so for some functions, you will have weights and biases, which are local minima, but that do not correspond to a local minima in function space. So if you reparameterize the function, you might not have a local minima anymore. So this is kind of a messy fact about neural networks. Okay, another application is that there is no lift of bounded rank matrices or tensors. So matrices, the set X is all matrices of rank less than or equal to R, or all tensors of rank less than or equal to R, and we need R here to be strictly more than 1. So bounded rank matrices or tensors where the bound is strictly more than 1, there's no lift satisfying 1 implies 1. And that's, if you remember the characterization for 1 implies 1, that was in terms of being surjective onto the tangent cone. So this is true because bounded rank matrices and tensors have some tangent cones which are not linear spaces. So at some of the singularities, there are tangent cones that are not linear spaces, and that automatically tells you 1 implies 1 fails. So there can be some linear cost functions on matrices or tensors, where if you lift those up via whatever parameterization you might have, you can find some parameters which are 1 critical, not mapping to one critical matrices or tensors. So that's an unfortunate fact. But if you remember, sorry, let me go back to this. I wanted to say more here. 2 implies 1, though, does hold for bounded rank matrices. Again, that's the LR transpose lift. So that's sort of a good lift for matrices, even though 1 implies 1 is never possible. Okay, some more applications. So the Burra-Montero lift, that was the lift where the space, I mentioned it in the talk, where the space downstairs was positive semi-definite matrices with the rank bound satisfying some linear constraints, and we parameterized it via RR transpose. That's actually a good lift. It satisfies local implies local. So one can argue that it's an open map. R goes to RR transpose. And it satisfies 2 implies 1. So here, some of this was already known, so this was previously known at rank deficient points or for specific cost functions, linear or convex cost functions. But what our framework contributed here is that you're getting these statements, local implies local or 2 implies 1 at all points for Burra-Montero and for all costs. So that's, yeah. Okay, so back to the LR transpose lift for bounded rank matrices. That one does not satisfy local implies local. So we saw it satisfies 2 implies 1, but it actually, it can trip up at local minima. So on the other hand, though, we can characterize exactly where things can go wrong for the LR transpose lift in terms of bad local minima. So LR can be a spurious local minima for some cost function if and only if it's unbalanced, meaning that the rank of LR transpose is strictly less than the rank of L and R. So we can also sometimes give precise statements about where these properties can break down, which points, which parameters they can break down at. We also have some strong negative results for tensors. So here on the bottom, I'm illustrating a tensor. So it's an array of numbers in this context with more than 2 indices. And a natural, so it's represented by this cube X here. A natural way to parameterize such a tensor is via a low-rank decomposition. So you can try to parameterize it by vectors AI, BI, CI, and map those vectors to AI tensor BI tensor CI summed over I. Right? And in this way, you'll parameterize low-rank tensors. Unfortunately, that lift and fails 2 implies 1. And in fact, any trilinear lift fails 2 implies 1. So, or any multilinear lift in at least 3 factors fails 2 implies 1 for bounded rank tensors. So most of the natural lifts based on decompositions that you think of for low rank tensors actually do not satisfy 2 implies 1. And we currently don't know any lift of bounded rank tensors satisfying 2 implies 1. Okay, so that's unfortunate. Okay, so there are more examples in the paper. Our paper is quite long, and most of the work is in applying the characterizations to various examples. So I mentioned sort of the most exciting ones in the talk. Maybe another interesting, sort of amusing one that we look at is a parameterization of the simplex. So you can parameterize a simplex by a sphere where the map phi is entry-wise squaring. So so x1 up to xn maps to x1 squared up to xn squared. That then the image consists of non-negative vectors, and the sphere constraint corresponds to the fact that the entry should sum to 1. So you do parameterize the simplex in this way by the sphere, and that's kind of an interesting lift. It satisfies local implies local and 2 implies 1, but fails 1 implies 1. So there's a few others in this table. But as far as the simplex goes, this lift in principle enables you to use smooth optimization for linear programs. You can, but yeah, we haven't been able to make that computationally efficient. Yeah, okay, so that's about it for the talk. As a summary, parameterizations are a natural way to deal with non-smooth constraints, complicated constraints. We introduced 3 main properties that are good for parameterizations. Local implies local, 1 implies 1, and 2 implies 1, and fully characterized these. And you can actually apply the characterizations to problems of interest. So thanks. This is the paper. Things I didn't talk about are the full characterization for 2 implies 1. We could talk about that offline if you wish. I didn't go through the details for the examples. Generally, they require some computations. And I also didn't mention that we have a procedure for taking a good parameterization of some set X, and in some cases producing a good parameterization for some related set. So we can sometimes build good lifts, starting from good lifts. Okay, so things we're thinking about. Are there any well-behaved lifts for low-rank tensors? Anything satisfying 2 implies 1. So we have negative results for any lift that arises as a factorization or more, but maybe you could have some other idea. We're not sure, and maybe it's possible to prove there exist no such lifts. When you go to apply our conditions to examples, you need to compute tangent cones, or at least bound tangent cones. Are there good ways of doing that? We found that this was often a bottleneck. It's also natural to study something like 3 implies 1, or more generally, k implies 1, though we haven't gone into that yet. And maybe most ambitiously, you might ask, how do parameterizations affect dynamics of algorithms? So here I've been discussing the static landscape and how nice points in the landscape on M map to points in the landscape on X. But what about the dynamics of algorithms? So that's probably a very difficult question, but yeah, an interesting one. So, okay, that's everything. Thank you.
Thank you, Joe. Any questions? There's none in the. I'll ask one then. So you said that rank K matrices are kind of nice. Have their manifold is not smooth because they're smaller rank matrices, right? What about rank 1? Because then there's only the 0th matrix.
Yeah, so rank 1 is a manifold. Rank 1 matrices form a manifold.
What can you say about
yeah, sorry. So let me be a little bit careful about that. So if you look at rank 1 matrices, they form a cone, so they have a singularity at the origin, at the 0 matrix. But if you look at rank 1 matrices in projective space, they form a manifold. So you don't need to, you don't need to lift that if all you want to do is get yourself in a smooth domain. You can just optimize over rank 1 directly.
Well, thank you so much for the talk. It was really nice, very intuitive, which is great. So when you mention spurious local minima, I suppose you mean local minima that are not global minima, right?
Yeah.
Do you? So if you're looking at your networks, we expect that to happen in any case, generally because we're interested in a populational quantity, right?
Yeah.
And yet it does happen. So in a sense, your message is pessimistic, right? Mm-hmm. But in terms of neural networks, we've been dealing with a pessimistic sort of theory for a while, and yet it kind of works. Mm-hmm. So for example, do you have any idea when you have these spurious local minima, how far? How bad could it get? Could it get extremely bad? Or in practice, would you expect it to be very bad?
So that will depend on the cost function f, how bad it gets. But let me also make one other comment. So where I said spurious local minima, what I meant was sort of an even worse case than I think what you have in mind. It's a situation where you have weights and biases, which are a local minima in parameter space, and when you map them down to function space, they're not even a local minimum there. So it's not like it's It's a local minimum that is introduced purely by the parameterization. And if you just sort of reparameterized your space of functions, it would go away.
Right. So, but the point is, if that does happen,
Yeah.
and usually, I mean, so I see you do work in very broad generality, right? But
Yeah.
we usually think of, let's say, at most 10 different cost functions in practice, right? And so for these 10 cost functions, you might expect that bad things don't happen, or at least if they were to happen a lot, we would have seen it before. So I guess for these reasonable cost functions,
Yeah.
if you do find a spurious local minimum, that is something that is a local minimum in parameter space, first of all, have you seen it and in practice? And then second, could they be very bad in terms of, if you stop your algorithm there,
Yeah.
how bad would it be in terms of your cost function?
Yeah, it's an interesting question. I haven't seen that, and I don't have too much to say about it, except that I think probably part of what makes local minima in practice for neural networks okay is the data distribution. So right, you have an empirical risk minimization, and the distribution of the data, I think, is extremely important in making it so that local minima are not very problematic in neural networks. And that's something that this work doesn't touch. So this work doesn't have much to say about your question, and I think to study that question, you'd need to dig into the specific cost functions and maybe the distribution of the data as well. Yeah.
I see. Thanks. Can I ask a follow-up question?
Yeah.
Okay. And so you mentioned a lot this, one implies one, or one generally doesn't imply one, and then two implies one, which is very interesting. Is there reason to expect, or would you expect there to be a condition that's weaker than two implies one? It's in between one implies one and two implies one, and if so, what could it look like? Because you do mention k implies one for k bigger than two, but I suppose you could look at other one plus some other condition implies one.
Yeah. Yeah, weaker than two implies one. I'm not sure off the top of my head, but think more about that. Yeah. Thank
Okay.
you.
Well, thanks, and thank you for the interesting talk.
I might have a last question, or maybe if someone's interested, can ask another one. But so, what about k implies 2 or something like that?
Yeah, it'd be great. It seems like it's something that won't happen very often. But indeed, yeah, one could study that.
Okay, if there's no more questions, thank you again, Joe, for the amazing talk. And you're free to ask questions. Is there a coffee today?
Thanks.
Okay,
Thanks very
so
much.
There's a follow-up cup. Okay, thank you, everyone.